promised at the beginning of this unit, today we're going to learn about imaginary numbers. So all numbers that you've learned up until this point have been in the real number category. That's why when we say domain and range, if it goes to infinity in both directions, is all real numbers, because everything we know, whether it's irrational, rational, fraction, decimal, whole number, integer, they've all been within the realm of real numbers. So as we were describing with our graphs the other day, when you have a parabola and it crosses your x-axis, those are your solutions or your roots for your parabola. We said that if there are instances where those roots don't occur, where you don't have the x-axis intercepts, we can't say that there's no solution. We can say that there's no real solution, but we did say that there were going to be imaginary roots. So today we're going to talk about how to find imaginary roots and what it means to be an imaginary number. So imaginary numbers are represented using the letter I. So I is equal to the square root of -1. So we've previously discussed how we can't take the square root of a negative number because no number times itself will give you a negative value. If you have a negative number times a negative number, that's going to give you a positive value. So we can't take the square root of a negative number in our real world values, but square root of -1 can be represented by the letter I. So let's just talk about some of these values, these exponents on our I. Anything to the 0 power, I to the 0 power is just going to be the whole number 1, because anything real or unreal raised to the 0 power equals 1. Okay, I to the first power equals the square root of -1. We don't know what the square root of -1 is in our real number system. Okay, I to the first power, we're just going to represent by the letter I. Okay, I to the second power is going to be square root of -1 times square root of -1, because I is the square root of -1. So we're going to do that times itself. Any number times itself under the radical is going to simplify to just that value. So I squared equals -1. Okay, I to the third power is going to be I times I times I. So right here we know I times I, or I squared, is -1 based on our previous work. And then times I. So this is just going to be represented by -I. So I have 1 positive I, -1 negative I. Okay, I to the fourth power, I times I times I times I. So here I have a pair of i's, I squared, which as we know from here is -1. Here I have a pair of i's, which when multiplied together gives me -1. -1 times -1 is +1. Okay, I to the fifth power, I. So I have I squared is -1, I squared is -1, and then I just have an I. I have that fifth I that didn't pair up. So I have -1 times -1 is +1 times I is just I. Okay, so what do we think the next one's going to be? Do we think it's going to be a -1 again? So I to the sixth power, I have I. Whoops, these multiplications are looking kind of like i's. So I have I times I times I times I times I times I. So I have a pair, which makes -1, pair, -1, pair, -1. So -1 times -1 is +1. +1 times -1 is -1. So that is going to be a pattern. 1 I, -1, -I. 1 I, -1, -I. 1 I, -1, -I. So anything that has an exponent of a multiple of 4, so 4, 8, 12, 16, 20, is going to get you that whole number 1. And then from there, you can count up your pattern I, -1, I. So for instance, I to the 17th power, I know 16 is a multiple of 4. So I to the 16th power is equal to 1, I need 17th power. So I need to multiply that by another I. So I to the 17th is just I. Okay, I to the 26th. So thinking multiples of 4, I to the 24th, because that's a multiple of 4, is 1. And then I need 25th, 26th power. I need to multiply that by an I squared, because I need 2 more values, 2 more integers on my exponent. Okay, I squared equals -1. 1 times -1 is -1. Okay, so don't let this freak you out so much. I just wanted you to have some exposure to higher exponents, but you'll realize that my solutions to any of these exponential I values always end up with just either a whole number, 1 or -1, or an I value, I or -I. So anytime you have an exponent on your I value, it can be simplified down to either an integer or a linear I term, meaning our answer is never going to have a exponent on your actual I number. Okay, so here if we look at the square root of -81, okay, we could rewrite this as the square root of 81 times -1. Well, we know that the square root of 81 is 9. We know that the square root of -1, from what we just learned up here, the square root of -1 is written as I. So we could say that our answer here is plus or minus 9I. So when we take the square root, we still do have to write that. We still do have to write that plus or minus in front of our value. Okay, 27. So I can write this as square root of 27 times -1 times x squared. Okay, 27 is not something we know the exact square root of. So I'm going to come right down here and I'm going to simplify that. So I'm going to divide by 3 and I get 9, divide by 3 again and I get 3. So here's my pair. I have 3 square root of 3. That's what 27 is going to simplify to. Okay, so here I have 3 square root of 3 for the square root of 27. And then I have the square root of -1 right here. Square root of -1 is going to equal I. So your I needs to come out here in front of the radical. So it's going to be right here next to the 3. Okay, it's customary to write that after your 3, just like any other variable. And then here I have the square root of x squared. So we can put that out here as well. Okay, and actually we should put the plus or minus in front. And I'm going to put 3x first and then the I square root of 3. Okay, here I have -16, which can be written as -1 times 16. Square root of 16 is 4, so I have plus or minus 4. Square root of -1 is I. And then I'm looking at square root of a cubed. So I have a times a times a. So this pair comes out. So I'm going to put an a between the 4 and the I, 4ai. Okay, I still have an a underneath the radical because this one does not have a pair. Then I have b to the 4th. So b to the 4th you could think of as b times b times b times b. There's 2 pairs. So that's going to be b squared. I'm going to squeeze it in here. Whoops, took way too much. Let's get a smaller eraser. Okay, so I'm going to squeeze it in here between the a and the I. So 4ab squared I square root of a. Okay, looking here, 2i plus 7i. So just like if I had 2x plus 7x, we can add those coefficients together because the variable part or the imaginary part matches exactly. This just simplifies to 9i. Okay, -5i times 3i. -5 times 3 is -15. I times I is I squared. So you'll remember I just said a while ago that we shouldn't have any exponents on our i's in our final answer. So I squared always equals -1 because it's square root of -1 times square root of -1. which causes that square root to go away. So we can rewrite this as negative 15 times negative 1, which is just a positive 15 value. All right, this example has 6i to the third power. So we're going to distribute the exponent. So I have 6 to the third power times I to the third power. Okay, 6 to the third power is 216. I to the third power, we could look up here and see that it equals a negative I, or, so this is going to be times negative I, which is going to be negative 216I, or if you don't remember what I to the third equals, you can write it as I squared times I, and you should memorize that I squared equals negative 1. So this is going to be negative 1I, or negative I. Now, complex numbers include both real numbers, so integers, and then imaginary parts. So they're written in the format a plus bi, meaning your whole number or your real number comes first, and then your imaginary piece comes second. So when we're just adding and subtracting, you would just combine like terms. You would treat the i's like an x. So you can combine things that just have regular i's on them together. Okay, here in the first example, we're just adding. So there's really no reason to have these parentheses because we're not distributing anything. So you could, if you wanted to, write it without the parentheses, if that makes you feel better. And then we're just combining like terms. So I have a 3 plus a 5. So 3 plus 5 is 8. And then I have a I and a 6i. So 1i plus 6i is plus 7i. And remember, we want our constant number first. So the 8 comes first. That's right here. And then the I piece comes second. We cannot combine the 8 and the 7 together and make it 15i because 7 has an I on it. The 8 does not. Okay, in this next example, I have a negative 3 up against the parentheses. So I'm going to need to distribute that. So I have 4 minus I here, and then I have negative 21 for negative 3 times 7. Negative 3 times negative 2i is plus 6i. So once I have that, I'm going to combine like terms. I'm going to do my constants first. So positive 4 negative 21 equals negative 17. And then I have a negative I and a positive 6i, which is going to give me positive 5i. Okay, this next piece, I'm distributing a 3i to everything. So I have 21i minus 6i squared. Okay, remember we can replace any I squared term with a negative 1. So this is really equal to 21i minus 6 times negative 1. 6 times negative 1 is a positive 6. So 21i plus 6. But remember, for our final answer, we want our 6 first. So this is going to be 6 plus 21i. Our next example, we have two binomials that we're multiplying together. So here we're going to have to distribute or use FOIL, if that's what you want to call it. So I have 5 times 5 is 25. 5 times negative 2i is negative 10i. 2i times 5 is positive 10i. 2i times negative 2i is negative 4i squared. Okay, so in looking at this, my negative 10i and positive 10i zero out. My I squared can be replaced by a negative 1. So this is really negative 4 times negative 1, which is going to leave me with 25 plus 4, or a whole number answer of just 29. So it's okay if your i's completely go away when you simplify, whether your I squared turns into a negative 1 or your negative 10i and your 10i cancel out and zero out. Okay, it's okay for you to have a whole number answer when you initially start dealing with i's. Okay, let's look at this example. So I have to distribute again. 4 times 5 is 20. 4 times 7i is plus 28i. Negative 3i times 5 is negative 15i. Negative 3i times 7i is negative 21i squared. So let's look at things we can simplify. Okay, right here, 28i minus 15i. So I'm going to start with this 20. So 20 plus 13i, because that's 28 minus 15. And then here, I have negative 21 times negative 1, because I squared, remember, equals negative 1. So negative times a negative gives me positive 21. And then I need to reduce down to my final answer. I'm going to combine together my constants, or my real numbers. I get 41 plus 3i.